Hypothesis test with larger samples. Example 7. A light bulb manufacturer tested n equal 50 of its light bulbs. In that sample, the proportion of defective light bulbs, p hat, 0 over 50. 0 divided by 50 is 0. Does this sample provide sufficient evidence that the manufacturer meets the industry standard of fewer than 10% defective? So the null value here is 10% as a decimal. 10 divided by 100 is 0.1. And the other null value would be the proportion of good light bulbs. It's 1 minus 0.1. And that's going to be 0.9. And we want to test H naught, P equal 0.1. The company does not meet the standard, versus P is less than 0.1. The company does meet the standard. So we're going to say the company meets the standard if there are fewer than 10% defective. So the key word here is fewer than. So that indicates a left-tailed test. And we want to check whether n times p0 is at least 5, n times q0 is at least 5. If so, we can use the z-table. Otherwise, we'll need to use exact binomial probabilities, such as a tree diagram. So our sample size is 50, and it's 50. 50 times 0.1 is 5, greater than or equal to 5, and that's a yes. And 50 times 0.9, 45, greater than or equal to 5, and that's a yes. So we got 2 yeses, and that means we can proceed to the next step and use the z-table. Otherwise, we need to compute the exact binomial probabilities. Z-table gives approximate probabilities, but they're pretty close if n times p0 and n times q0 are both at least 5. Okay, so our expected value, the mean of p hat, if H naught is true, if there are 10% defective, then on the average p hat should be the same as 0.1. It would also be 10%. On the standard deviation of p hat, square root of p0 times q0 over n, so that's 0.1 times 0.9 divided by our sample size, which is 50. And that comes out to be, you do square root and then 0.9, 1 times 0.9 divided by 50 on the calculator, comes out to be 0.042426407. So our test statistic, it's a z-score. It's basically a variation on what the same formula we were working with earlier in the semester, except now it's applied to this situation. It's a score minus the mean divided by the standard deviation, but the score in this case is going to be our sample proportion, which was 0, and the mean of p hat 0.1, and divided by the standard deviation of p hat with 0.1. We already computed that. 0.1 times 0.9 over 50. So that's going to be, do the subtraction first. It's negative 0.1, and we already computed this thing here. It's the 0.042426407, and do the division, and that comes out to be a negative, approximately negative 0.236. Sometimes the formula is abbreviated. They don't bother with the P0 and the Q0. If it's clear that you're working with the null values, you can save some handwriting if you just leave off the zeros. Just keep in mind that this P here in this context, we want it to be the null value of P. So it's going to be and the null value of Q. So you can do it without, you'll see it sometimes written without the subscripts there. But it's the same formula, it's the same computation. And we get a z-score of negative 2.36. Because we're doing a left-tailed test, And because our table is our z table is left-tailed, we want to look up the same sign as our test statistic. So we want to look in row negative 2.36 of the z table. We want the probability z is less than negative 2.36. So the picture looks something like this. Z-score of 0 is in the middle. Negative 2.36 is pretty far out there. And so we want this part of the bell curve. And the probability corresponds to the area of the shaded area there. So we want to look in row negative 2.3, column 6 of the z table. And that comes out to be 0.0091. So that's our p-value. And this is a left-tailed test, so we don't need to multiply by 2 here. That's going to be our p-value. And it's less than our desired level of doubt, with 0.05. So that means we reject H0 and conclude the company does meet the standard. So we could also do this using the exact binomial probabilities. Usually, if we meet the standard for the z table, we'll use the z table because that's usually more convenient. But it is possible, in this case, to compute the exact probability. There's only one path from the tree diagram where all 50 light bulbs are good. So it's going to be 0.9 times 0.9 times 0.9, or etc., or 0.9 to the 50th power. And if you do it on the decimal, you get a p-value of 0.0052. And that's provides even stronger evidence, even smaller than our previous p-value. Keep in mind the p-value is the probability of making an error, so you want that to be small. And so this is even provides even stronger evidence, 0.005 compared to 0.009. And that concludes this presentation.